So now our next topic is we are skipping this salt hydrolysis. Yes, we will come back to it. And today we are going to discuss on this Lewis acid and base concept. Yes, and this is really a very important definition. Uh, Earlier we came to know the two definitions of acid and base that is given by like Arrhenius and Bronsted. Yes.
Mhm.
So can you tell me what Arrhenius said?
Um, he said that acid,
Yes.
uh, when it's dissolved in water, it gives H3O.
Plus, yes, it gives hydronium ion or it gives H plus. Correct. And what Bronsted said?
Uh, Acid is a proton donor,
Very
and
good. Acid
base
is a proton donor and base.
is a proton acceptor.
Wow, excellent. So these were the two definitions that were coined by these two scientists. But here now another scientist came like Lewis, which we are saying. So he just said a definition which is out of the box. Now before telling the definition to you, okay, let me take you to another concept of chemical bonding because you need to understand that concept to understand the definition. Okay,
Mhm.
so we are going to discuss like this molecule, the boron trifluoride. So if we go to the Lewis structure of this molecule, I may write it as like B, F, and here it is F, and here it is F. Correct?
Yeah.
So it has a planar structure, and you know like fluorine is containing 7 electrons in its outermost shell.
Mm.
One is shared here, and boron is having only 3 electrons in its outermost shell. Like boron is having configuration of 2 and 3, and fluorine is having configuration of 2 and 7. And both are in the race of getting like their octet complete.
Mm.
Yes. So like fluorine wants to take 1 electron and complete its octet to get a stable electronic configuration. Similarly, boron also like trying to get 4 or 5 more electrons to complete its octet. Yes. So both are in the same boat. So when there is a like electronegative difference between the compounds, normally like if it is less than 1.7, then covalent bond is formed. Okay, this is the trick. Okay, so boron and fluorine forms a covalent bond. So in the covalent bond, this is formed by like mutual sharing of electrons. Like here, 1 electron of boron and one from the fluorine is shared. Yes, you can
Yeah.
see here, like I have drawn in the middle. And now, if we do like this activity, yes, you know, like fluorine, like this thing. Now, fluorine after this bond formation will be having how many electrons? 2, 8. Yes, the electronic configuration of fluorine after making bonding with boron, it will change into 2, 8, like its octet is complete.
Yeah.
And this is the case with like almost like all fluorine. Yes, here also you can draw the remaining ones, 6 electrons. So fluorine is like completing its octet and it's pretty much happier with this sharing. Now, what
Mm.
about boron? Yes, that is the important issue, boron. So if I count the electrons of boron, I will find like boron after the bonding, it is having only 6 in the outermost shell. You can check.
Yeah.
2 plus 2 plus 2 is 6.
Yeah.
So it means still it is too short of octet, correct?
Yeah.
So it means it is not like happy. Yes. And
Mm.
those species like in which like there is like a deficiency of electrons, like in this boron trifluoride, are known as electron deficient species, correct?
Yeah.
Now, and also these species are also called as, there is a special term given to it, is known as electrophile. And if you break this definition, electrophile, this electro means electron and phile means loving. So these species are like seeking electron pair. Yes. Why electron pair? Because it needs 2 electrons. So I am talking about a pair. Pair means 2 electron. So these species are known as electrophile. Correct?
Yeah.
Is this clear to you? Okay. Now let me take you to the another example, that is a case of NH3, that is ammonia. Ammonia is also having not like this structure, it is having a pyramidal structure. We have to draw like this. Why? Because it is having a lone pair as well. And what lone pairs are? Lone pairs are like the electron pair that are not involved in bonding. Okay, this is a lone pair which are not involved in bonding, lone pair. I hope like you know this.
Yeah.
And if you check out the nitrogen, nitrogen initially it is having 2,5 and hydrogen is having only 1. Okay, so hydrogen is looking to complete its duplet by getting 1 more electron, and nitrogen obviously wants 3 more electrons to get happy. So fortunately, like both are in the same boat, and I can say like if I draw the electrons of nitrogen like this, and the hydrogen by the yellow. So after this, like I can say like this bond is formed, this bond is formed, and this bond is formed by sharing. Yes, and both are happy here. Hydrogen is completing its duplet. Yes, and nitrogen on the other hand, if I draw a bigger circle, nitrogen is completing its octet. You can count it, it is having 8 electrons after the bonding. Nitrogen is like 2, 8 now, and hydrogen is now happy with 2. Is it clear?
Yeah.
Now these species in which there is excess of like electrons, like this is unavailable and this is lone pair. Yes, it is not taking participation in any bonding. This this molecule is called as electron rich species. Correct? Electron rich species. Why this is electron rich? Because it is having lone pair. Yes, excess of electrons, and lone pairs are those which do not take participate in bonding normally. So there is again for this species as well, there is a common term which is known as nucleophile. Because they are having more electrons, so they are seeking for nucleons like positive charge. Okay, so that they can share. It's similarly like if you can take an example, suppose if somebody is it's a very rich person, like suppose Bill Gates. Yes. Now suppose somebody is a poor. Yes. Now if it is a very rich person, he has ability to donate some of his money to this poor person. Correct?
Yes.
Now the richness in terms of like chemistry is considered in terms of electron. So somebody is having excess of electrons, like more lone pairs, is considered to be rich. However, someone which is short of electron is considered as poor. So obviously rich can easily donate to poor.
Yeah.
But the reverse is not true. Yes. Is it clear? So this is a very simple phenomenon we see in daily life as well. Okay. So richness is only like not by money, because they are not interested in money. They are interested in like doing business with electrons. Yes. That's all chemistry is all about. Okay. So now what Lewis said. Lewis said an acid is lone pair acceptor. A base is lone pair or donor. Or I can also write like instead of lone pair, like it sounds bad, you can use electron pair.
Mm.
Correct?
Yeah.
So can you tell me out of these two, like boron trifluoride and NH3, which is an acid? Like see, usually we know like acid gives H plus or H3O plus and so and so and so. Okay,
Mhm.
lot of definition. But now here on looking at boron trifluoride and waiting for boron trifluoride to give any H plus is nonsense. Yes, no H plus
Yeah.
is going to come out of boron trifluoride. So how can we decide like this boron trifluoride is like acid or a base?
Mm.
So we have to take help from the Lewis statements. So can you correlate this and identify which one is Lewis acid or base?
So acid should accept electron pairs.
Yes,
So I guess NH3.
NH3. So why NH3 needs electron pair? There must be some reason.
Mm. Wait, so this is lone pair, so it's extra.
Yes, this is extra.
So this should be a base.
Yes, exactly. Very good. This should be a base because it is already rich. So
Oh.
electron, yes. The one who is seeking electron should be deficient.
Mm.
Yes,
I-
got it. So only the
Yeah.
poor people looks for money. Rich people generally have like great heart. They also look for money, but they have ability to donate. Yes,
Yeah.
they're not interested in making more money. It's natural, like more money comes to them. Okay, it's strange. Okay, so now it's just like someone who is thirsty will go towards water. Yes,
Mm.
or towards the like lake or river.
Yeah.
So this will be an acid, Lewis acid, not acid, Lewis acid, and this will be a base, Lewis base. Correct. Make sure like you write Lewis before this. Yes.
Oh.
Yes, because otherwise Lewis will be unhappy. Yes, you know. And
Mm.
scientists, you know, like they are very arrogant. So now you have known this concept now, but why? What is happening? Like in this, like how this is acting like as an acid, and how the NH3 is acting like a base. We will look upon it. Okay. So suppose I have having boron trifluoride. You know it's electron deficient. I can write like electron deficient here. Clear? And suppose if I am having NH3 here, I can write like it is electron rich.
Mm.
Electron rich. So rich donates to poor. So what happens here? This lone pair is donated by this NH3 to this. Now I can say like boron trifluoride is accepting this electron pair and nitrogen or the ammonia is donating this electron pair. So this is a like I can write like lone pair acceptor. Correct?
Yeah.
And this one I can write like lone pair donor. Or you can also rewrite it as lone pair is or this lone pair can also be like written in a better way like electron pair.
Mm.
Yes, means same, almost same. So because this is like a lone pair acceptor, it can act as a Lewis acid, correct? And because
Yeah.
this is a lone pair donor, it act as a
Lewis base.
Lewis. Very good, Lewis base. Okay, now what happens when we do this reaction or like this bond formation? So I can write like NH3, and here is a bond, then BF3, or you can write like this bracket, and this is known as adduct. Okay, like this. And in some book, like there is some arrow like this. Okay, but this is like a new compound formed out of this. Clear? Is it clear to you?
Yeah.
Now it is the most difficult of like you can easily identify which one is acid, which one is base by looking like H plus or OH minus or like so and so and so. But when some is not showing like what they are, it's hard to identify. Yes. Suppose if I give you another example, can you spot out like which one of this is a Lewis acid? AlCl3 or H3O plus? Or I write like H2O. Which one is a Lewis acid and which one is a Lewis base? It's really hard to identify. So what you should do, you should just take help from chemical bonding, and then you just draw the structure like this. Yes,
Yeah.
you have to recall that portion, and then you can easily like tell which one is acid and which one is a base, Lewis acid base.
Okay.
Can you do so?
I guess.
It is the toughest, like no idea whatsoever. Or you should have a good memory.
Yeah.
So do you have any answer?
So Al aluminum has 3.
Yes, 3.
Yeah. So
Yes,
and chlorine has like
7.
7.
Yes. Then so aluminium has 3 and chlorine has 7. So there are
Yeah.
3 chlorines. So getting 1 electron from each chlorine, 3 plus 3 is 6. So this aluminium will be having 6, just like boron. It is also like, because aluminium is like comes just below the boron. See, boron, aluminium, gallium, indium, and thallium. Yes.
Yeah.
So all elements like are in the same boat. Yes.
Yes.
So they do show the same property, like they must act as a Lewis acid usually. So this is like electron deficient, correct? And however, this H2O is electronically rich. It is having 2 lone pairs.
Oh.
So what will happen? This H2O can give one of its lone pair to this aluminium. And this will act as a Lewis base. This will act as a Lewis acid. Correct? So the other trick, like if you can find out whether a species is having some lone pair, so it might act as a Lewis base. And the other one is Lewis acid. Yes?
Yeah.
Okay.